go?
I'm good to go and record as we speak.
All right. So, welcome to the Lehigh Valley Amateur Astronomical Society. My name is Mike Hubert, for those who haven't met me yet. I'm currently serving as the director. So today we have a very special presentation for you by Charles Bracken. He is an astrophotographer and he's written several books about the subject. So he is an excellent author in my opinion. I have most of them. So without further ado,
Great.
Charles Bracken.
Thank you so much. Yes, I'd say the only person who loses when I sell books directly is Amazon, right? So they take most of the profits for me. Yes. All right. So tonight, I'd like to first of all say thank you for having me. It's great to be here. It's actually my first time here. Which is sad because I only live 45 minutes away. So love to come back at some point, but great to discover that there are observatories tucked around the hills all around Pennsylvania. So I image from Bucks County. This is a very light polluted area. But does anybody recognize what we're looking at here, this nebula? I'd be really surprised if anybody does. I took this actually a week and a half ago. So this is the Longhorn Nebula in Cygnus. It's that bright patch right in the middle of all the nebulosity of Cygnus. I think it goes by IC 1318A. But I just wanted to throw up, this is just a recent image. You can image from this area with all the light pollution, but I do a lot of narrowband imaging for that reason. So maybe we'll get into that a little bit. These are the books that I've written. There is me, actually I'm not in the picture, but that is my happiest time right there, right? I imagine it is for a lot of you. It's twilight, sun is setting, the sky is clear. You are about to have a good night. In my case, years ago it used to be probably not going to get a lot of sleep, but I've got everything automated in my backyard now, so I'm going to get set up. I can get set up in 10 minutes, be back inside watching Netflix, check on it, and then sleep a good night's sleep, wake up the next morning, all my data's there. I've gotten it down to that now in my backyard, but it's just so nice when you're out there and it's quiet and calm and it's clear. Those are my websites. You can see me on Astrobin, my email if you want to reach out, deepskyprimer@gmail.com. But this is why I'm here this evening. I just wanted to talk with you about some common questions people have when they look at an astrophoto. So they're wondering, like, what am I looking at exactly? What is this made of? Where is it? How far away is it? How do they take these pictures? Where can I find this in the sky? So we're going to cover a lot of these questions tonight. But first, let's talk about astrophotography in general and how far we've come. So the state of the art in 1895, right? This was probably a wet plate glass exposure. It's like on a glass negative. This is a 6-hour exposure that E. Bernard took. That's the California Nebula. That was, an amazing exposure at the time, right? This might even be, if I'm not mistaken, this might be one of the first to reveal the full extent of the California Nebula there. My backyard in 2021, with a couple years of practice and some decent equipment, I'm able to do that. So things have come a long way in 130 years or so. The image that inspired me as a kid, so I was in first grade when this National Geographic came out. That was by David Malin. I think he took that from the Kitt Peak Observatory. And I saw that and I thought, wow, I want to be an astronomer. That did not happen, by the way. Actually, I went to school microbiology and then ended up in business somehow. But I decided at some point, though, I was going to, even if I couldn't be a professional astronomer, I wanted to take pictures like that. And again, look at the difference, right? So this was state of the art. I mean, David Malin pioneered color astrophotography. This was a very big deal in the 1980s. From my backyard, right? I mean, this is this is almost trivial now. Like, not trivial, but it's it gets pretty easy to take a picture of something like the Horsehead Nebula. The big change between even the 1980s and now has been electronic sensors. So film was only recording 1 to 3% of all the photons that would strike that negative. Most cameras these days are 60 to 80% efficient, right? We call that the quantum efficiency. So you were just wasting photons because they had to strike the silver, just right to cause a chemical reaction. No, a sensor is going to record almost everything that comes into it now. So as a result, you've now got electronic cameras that are an order of magnitude more sensitive than what they had in the 80s. So I don't know how long David's exposures were here, but I think that was 6 hours or so, something like that Horsehead Nebula picture. Before we get into a lot of the pictures, I just want to say a word about scale, which is something other genres of photography don't have to deal with as much. But in astrophotos, you don't have a sense of depth, usually. And you don't have something there for comparison to get a sense of how big the thing you're looking at is. And when I say big, I'm not necessarily talking about how physically big it is, but how angularly big it is, how big it appears to us in the sky. So I've just put up here two commonly imaged objects, right? So there's the Ring Nebula on the left, there's the Andromeda Galaxy on the right, both beautiful objects. But when you look at all these photos, you can't always tell how big that thing is, almost like how much magnification almost, if you will. So what I did, I took these two images and I laid them out so that they'd be at the same scale. So that's how big the Ring Nebula is if it's not there in the sky. I just placed it there. This is a Photoshop trick. But there it is compared to the Andromeda Galaxy. And I put the moon up there for scale as well. Right? So the Andromeda Galaxy is over 3 degrees across. The Ring Nebula is 1.75 arc minutes across, right? But just know that you're looking at images that were taken with a lot of different telescopes here because, and this is for those of you who might have to get the purchase of your next telescope approved by your spouse or significant other, you need lots of different telescopes to zoom in on these different objects, right? You need one type of telescope for the Ring Nebula, you need a totally different type for the Andromeda Galaxy. Okay. So I'm going to use this framework we're about to go through. So this is my Charlie's taxonomy of deep sky objects. But I think this is helpful. It's a helpful structure for us to talk about what it is you're actually looking at when you look at a deep sky object. And at the highest level, you can break this down into things that are made of stars and things that are made of gases and dust. We call the things on the right, the gas and dust things, those are nebulae, right? The things on the left, there's 2 different parts to those. So things that are made of stars can be galaxies or star clusters, depending on how many stars you've got. And the things on the right, you might be looking at gas that's been ionized or gas that's not ionized. We call it just dust, or we call those molecular clouds. If we break it down further, this is the full taxonomy. This is what we're going to go through tonight. So, galaxies come in several different types. We'll talk about those. Star clusters, primarily we speak of them in 2, globulars and open clusters. The nebulae, we've got ionized nebulae, so these we'll talk about what happens there, but those are emission nebulae, and then we got planetaries and Wolf-Rayets and supernova remnants. Then we've got the dust and molecular gases. Those are where the starlight is just being reflected off. The gas isn't actually being ionized, but you're just getting reflected light. But this is a nice way for us to talk through today what you're looking at. So let's start by just giving us a sense of distance. So everything in the box here, this is all stuff in our own galaxy. So unless it's a galaxy that you're looking at something in the Milky Way, right? So that's the other crazy thing about astrophotos when you're looking at them is the difference in distance between all the things here on the right and galaxies is orders and orders of magnitude, right? So you're looking at things, if you're looking at any of those things, if it's not a galaxy, it's in or in orbit around our galaxy. So it's, probably no more than 50,000 light years away. If you're looking at a galaxy, that is way further away, right? So that is at least millions, if not billions of light years away. And also much, much larger of a thing. So those galaxies, probably most of them have all their own. They've got their own clusters, they've got their own nebulae within them, right? But they're just so far away, we don't often get to see them except for the closest galaxies. The only exception to this rubric and everything I just said, there are some galaxies that are in orbit around ours. So the Magellanic Clouds, there's a couple small dwarf galaxies. Those are technically around our galaxy, and they are their own little galaxy. But most galaxies, like the first major galaxy you think of that's closest to us, it would be like the Andromeda galaxy. So that's, what's that, 20 million light years away. Okay. So if we, sorry if I'm pushing the wrong button here, but can you advance to the next slide for me manually?
Should work now.
There we go. Okay, let's talk about galaxies. So there's the one you've seen, and this is, if you're going to take a picture of one thing in the night sky, this might be the thing, depending on what time of year. So if it's, winter, spring, this is the thing you're going to want to take a picture of. But it's huge, like we saw, it was 3.5 degrees across. You're actually going to need a fairly short focal length telescope, and hopefully a large sensor to capture it. But you can see this one through a telescope with your eye, but if you attach a camera to it, wow, right? It really pops. Those dust lanes come out. And this, of course, takes a little bit of processing. This is not just, as it comes straight out of the camera. But you'll observe, it has a couple of galaxies in orbit around it, right? So you've got M110, M32. Those are little galaxies that are in the orbit of M31. And they don't show up well in this picture because I didn't add hydrogen alpha. But this galaxy has its own nebulae within it, right? So there are star-forming regions of ionized gas and nebula within it. Maybe a better example of seeing nebulae within another galaxy is M33, which is here. So that's the Triangulum galaxy. So you can see there we've overlaid H alpha into this one, and you can see all those reddish orange patches in there. Those, if you lived in the Triangulum galaxy, you would look out in your night sky and see these gigantic emission nebulae in your sky. M51 down there, another great example. These are all spiral galaxies. Right? So this is the classic form. I think almost half of the galaxies in the universe are thought to be spirals. Right? So you've got a huge cloud of dust. The dust by under its own gravity starts to collapse into stars, but the stars are then sort of forming and spinning around. As it pulls inward, you're getting hundreds of billions of stars in these cases forming into a flat plane, and you end up with a nice spiral galaxy. Obviously, I think these are the prettiest for pictures. They present to us these are what we call face-on, like especially M51, that's exactly face-on to us. They also present to us edge-on, and this is what they look like. This is pretty much what we would expect the Milky Way to look like if we could get far enough away from it to see it. So there's the Splinter Galaxy and NGC 891, and you can see a lot of them have a prominent dust lane, like slicing right down the middle. All that interstellar dust that either didn't form into a star or was a star that exploded, and you've got this dust in there is obscuring the light from all the stars in them. So you get these nice cuts right across the middle. And there's lots of examples. The Hamburger Galaxy, the Sombrero Galaxy, are these edge-on spiral galaxies, and you can see that nice lane. Sometimes they come in variety packs. So this is the Draco trio. This is in Draco, but you've got here an edge-on, nearly sort of oblique face-on almost, and then an elliptical galaxy in the middle. So elliptical is the other type of galaxy we should talk about. These don't really have a nice spiral form like that. So I think you talk to an astrophysicist, my understanding is they're generally thought to be where the result of a prior collision that disrupted that, and now instead of all the stars moving around in a circle, they're just sort of moving almost randomly, but they're still gravitationally attracted to each other, and you've got a lot more random motion, and what you end up with is this sort of structureless shape like that. From an astrophotography perspective, I don't generally chase after them, not the prettiest looking things, generally looking for the spirals, but they are much, much older. Those tend to have much older stars in them, so astrophysically they're certainly very interesting. The third type of galaxy we should talk about are irregulars. Most of the time you've got an irregular galaxy because two galaxies have collided or were about to collide. So here's the whale galaxy and the hockey stick, we call them. And if it shows up there, you can kind of see it in the screen. The hockey stick on the right, you can even see, obviously it's been disrupted. It looks like it was a nice edge-on spiral, and it's been disrupted. And you can see below it there, this like tidal tail of stars, a streamer that's been just ripped off, right? And those are just sort of, floating out into space. And it's fascinating to think that when galaxies collide, and of course this takes billions of years, right? This is something that unfolds over an extremely long time scale. There's so much empty space between the stars that they're essentially passing through each other. So these are like gravitational collisions, but it's not like the stars are actually banging into each other. I think I saw somebody calculating like the odds of a single star in two galaxies of 100 billion stars colliding is something like 1 in 1,000 collisions would result in an actual collision of a star. Like they're mostly empty space. They're like, then you can think about that. Think about how far it is to the nearest star, right? It's 4 point something, light years away to Alpha Centauri. There's a ton of empty space, and then you've got multiply that by 100 billion, and you get a whole galaxy. So the two are kind of passing through each other, and when they do that, you see they just rip. It looks like it rips these pieces off, right? You're just disrupting their orbits and their momentum. These images, by the way, none of these are professional. Every single one of these images either I took or I took in collaboration, and I put Max Whitby and Charles Pevsner are the two people I image with the most because we share a telescope in Chile, where I don't have Pennsylvania sky, so I can actually image things like galaxies much, much easier. Here are two famous galaxies. These are known as the antennae. And you can see they are in the process of colliding right now, right? And you can see just the streamers of stars that have been ripped off, just thrown out into space. Use your imagination. I always like to imagine like if there are planets that are habitable and there are entities on those planets, and they were part of a galaxy, and now granted these unfold over hundreds of millions and billions of years, but interesting to think you could be on one in a galaxy and then thrown out of the galaxy. I don't think those stars are coming back into those galaxies anytime soon. The other interesting thing, and I think if you've seen the Hubble Deep Field image, it was a great demonstration of this. But even as an amateur, you get the same effect. But if you point a telescope at an empty patch of sky, there are a lot of galaxies out there, like almost everywhere you look. And granted, they tend to be within our line of sight, kind of in certain clusters. But this is a galaxy. So I just took this image like 3 months ago. This is from our scope in Chile. This is just a 5-inch refractor. Like this is not some massive scope. There's IC 5201. That was my target, and I looked up what's nearby. I thought rather than put it in the center of the frame, oh, there's some fun little galaxies over there. I'll capture it so I can put them in the same field of view. That'll make a pretty picture. And sure enough, right? So I looked that up. That's the brightest one in the middle there is ESO 28-9, and you can tell when they get out of the NGC catalog and the IC catalog, you're starting to get into some obscure stuff. I don't know how dim they are, but they're magnitude 16, 17, something like that. Then I look at the image, and when you're in an area of the sky like this, a lot of things that look like stars turn out to not be stars. So this one I had to look up as well, certainly. That's a whole cluster of galaxies. There's like 50 galaxies in that little patch. So every one of those little dots that looks like a star, it's called ACO 3862, Just a side note on catalogs. So you've seen most of what I've shown today had an M designation from SEA. Charles SEA discovered, he actually didn't discover most of the objects in that catalog, but that's the most famous catalog, the 110 objects that he didn't want to mistake for a comet when he was looking for comets. You probably also see the NGC catalog, the New General Catalog. The IC catalog, so if you see NGC or M, it was discovered visually. IC, the index catalog, was the first catalog in the late 1800s. Those were mostly discovered photographically. So that was the beginning of the photographic era. So everything that doesn't have an NGC or an M designation pretty much in the night sky was discovered photographically. And it's super impressive given I told you how inefficient film photography was. You're throwing away 99% of all the photons that strike the negative. And they still were able to take amazing pictures, and they captured the whole sky multiple times over and documented all these. So this IC was one of the early entries into the southern hemisphere part of the IC catalog. Anybody recognize this? This is famous.
Markarian chain.
Exactly, Markarian's chain. A really cool collection of galaxies, part of the Virgo supercluster when we look toward Virgo. Like I said, I'm not usually interested in imaging elliptical galaxies because they just look like a big fuzzball. But in this case, when you got a lot of fuzzballs, you got a couple spiral galaxies thrown in there for fun, it actually makes a much better, more interesting image. But this is a wide field. This was taken with the 4-inch refractor wide field image of Markarian's chain. Okay, so that's a lot about galaxies. So that's when you have on the order of 100 billion stars. But if you only have a couple 100,000 or even a couple dozen stars, you get something smaller. You get a star cluster. So this is one of the most famous, at least for us in the northern hemisphere, this is our biggest and brightest globular cluster out there. This is the Great Hercules cluster, M13. Pretty cool though, it's got a little galaxy in the background. And it's interesting to think when you see an image like this, that cluster is, let's say, right in front of your face. That galaxy is like 100 miles in the distance, right? And just way, 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 way bigger, right? So that cluster is in our galaxy. That is a whole other galaxy. So we're talking, thousands of times further away. So they just happen to be in the line of sight. Open clusters. Again, I'm an astrophotographer, so these don't usually make my hit list of things, and this is why. So this is M39. I think these are the kind of objects that actually look better through an eyepiece. A lot more interesting through an eyepiece, probably most of the time than in a picture. But sometimes, not all open clusters are bad, and they can be in very interesting combinations. Sometimes you get a nice alignment, like this one. So this is M35 and NGC 2158. I like this. Very, it's kind of a dense open cluster, and you've got another. I don't know if that counts as a globular. This is probably just a dense open cluster. But you kind of get a sense of depth, right? Like that one on the right. It's a little further in the background. So it makes kind of an interesting picture. But I mostly image star clusters when the moon's out, and they're just something you can image when the moon's out, and that's usually when I tackle those. Okay, let's talk about gases. Ionized gases in particular. So all the things in this column, so these are all nebulae where the gas is ionized. And I would liken this to a neon light, a proper neon light, right? So an actual tube of gas that is being energized, and it is emitting light. It's not emitting broadband light, though. It's only emitting at very specific wavelengths of light. In fact, you've got a poster over here. I see if you do spectroscopy, you can use this to determine what kind of gas you're looking at. In fact, William Huggins in England was the first person to do that, to show that some of these objects they were not emitting light at all wavelengths. They were emitting only certain ones. And so if you have a lab, you can try to ionize gas in the lab and see what wavelengths it emits at. And then you can compare that to the sky and figure out what exactly you're looking at. So these gases are all ionized. That process, we don't have to go into the physics of it, but basically you've got hydrogen out there in the universe. So the vast majority of atoms in the universe are hydrogen. It's the simplest element, right? One proton, one electron. Hydrogen likes to be molecular hydrogen. It likes to be two hydrogen atoms stuck together, but it can be out there just neutral hydrogen, just one hydrogen atom. If an atom like that is hit by UV radiation from a star, it literally has enough energy to pop that electron off there. But now you've got this soup of protons and electrons floating around. The electrons get recaptured by the protons. When they get recaptured, they have to throw off that energy. In order to get to a lower energy state, they have to expel energy. They expel it in terms of photons. They only expel very precise amounts of energy, which corresponds to precise wavelengths of light. That's the process that's happening here. So you get, effectively, glowing gas in space. You get like a neon light out there. And it's not a matter of how bright the light is, remember. It's a matter of the wavelength of it. So the photons have more energy the shorter the wavelength. So it has to get to the point where it's out of our visible spectrum and into the UV spectrum where it has enough energy to actually do this. So what you have are young hot stars that are emitting ultraviolet light, and that is powerful enough to discharge or to free these electrons. And then when they come back in, you get this glowing gas, like a neon light in space. So let's first look at the first type of those, emission nebulae. These are the most common. These are patches of hydrogen out in our galaxy, and they are near an ultraviolet star. This one is not imaged very much. This one's actually in great position right now if anybody wants to image this. This is in Cygnus. This is LBN, Lens Bright Nebula 331. Looks a lot like the Witch's Veil Nebula, I think, but it's just a cooler one. And you can see that almost magenta red glow, right? That is the specific frequency around 650 nanometers that hydrogen glows at. Other gases are being ionized, but hydrogen is by far the most prominent of those gases. There's just so much more hydrogen out there. So this is what this one looks like. This one's called a Boogeyman Nebula. So this is an Orion. This is a winter nebula. You see all that ionized glow right there. That's all hydrogen gas. Now, the dark part is actually where you have molecular hydrogen. And we'll talk about those in a couple minutes. But that's where you have hydrogen and dust in there that is obscuring the light. So the gas is probably glowing behind it, but it's being obscured, and so it leaves that shadow. Now, a lot of times you're going to see images like this. If you see an image of a nebula, you're going to see something like this very often, especially from amateur astrophotographers like me. This is what we call a matte color image. So I mentioned that hydrogen is by far the most common element out there in interstellar space. There are also other elements. There's a little bit of oxygen, a little bit of sulfur. There's also carbon monoxide, a couple others, but the ones that, when you ionize them, that they emit in the visible wavelengths that we can actually see, we typically use hydrogen, oxygen, and sulfur. And so we combine filters for those that filters out all the light and only lets through a tiny sliver of light at just the wavelengths that these guys emit. We then can take them and map those colors to create an image like this. So what you're seeing is representing something in reality, in the sense that the blue is showing you where the hydrogen is, and the yellows and oranges are showing you where sulfur and hydrogen are. But these are not the colors that they are actually. So you may be familiar with how a regular image is produced, what we call an RGB image, right? So we can take the visible spectrum and group it up into sort of the left third would be red, the middle third would be green, the right third would be blue. We create filters that only let those in. You take a black and white image of each, then you can synthesize those into a color image. This is how all color photography works. If you do the same thing, but instead of letting a third of the spectrum in, this is an example like what an H-alpha filter would do, you're just letting in one narrow wavelength of light. And you do the same thing with a different wavelength of light for sulfur and a different wavelength of light for oxygen. And then you do that same recombination process where you say, I'm going to make, in the final image, you're going to be red, you're going to be green, you're going to be blue, right? You get this. But the key thing to note is that those gases aren't actually glowing with those colors. So it's physically true, and it's representing where those gases are in an image, in a narrowband matte color image, but in different colors. And the reasons for that, mostly because sulfur and hydrogen both glow at a deep red, so they'd be indistinguishable. So we sort of map them to different colors to make them more distinguishable. This is what it looks like. So this is Sharpless 284. This is in the southern hemisphere. I took this with Charles Pevsner. Kind of an underrated nebula, I think. It's really pretty. But I actually took the hydrogen, sulfur, and oxygen images and I put them on the side and I inverted them to make it a little easier to see where they are. And you can see hydrogen is actually the brightest. Sulfur is pretty faint and it kind of appears around the outside, the boundaries of where the hydrogen is. And then oxygen, much more diffuse and more throughout. And then when you map those red, green, and blue, or I guess in this case it'd be green, red, blue, you get an image like that. So that image is scientifically true, but not true color. And you'll see a lot of images like this, especially as there's more light pollution in the world. Honestly, for my backyard in Bucks County, I do 90% of my imaging this way, because by using narrowband filters, I'm blocking out almost all that light pollution. These objects are only emitting light at one wavelength, so I only want that one wavelength, but the light pollution is all of the spectrum, and so I can cut through that. Galaxies, I can't really do that for them. There's no filter that can block that out, because the light pollution is emitting at all wavelengths as are the galaxies. There's no way to make that go away. You really need dark skies to get great images of reflection nebulae, galaxies, broadband targets like that. So that, for those of us who image from an urban area, or suburban area, narrowband imaging is becoming more popular. Just another example, so this is, south of Orion there, so this is the Seagull Nebula. I love this guy. These are Sharpless 222 and 224. I think people have called that one like the Chef's Hat Nebula, maybe. This is I think it looks like a lion myself. I saw a lion the first time I saw this. Other people see maybe a yippy little dog. Some people see nothing. But this is Sharpless 132. I think it's a particularly cool little nebula. This is was this 20 panels? I think this is a 20 panel mosaic that I took last summer. This was my project for all summer of last year. I didn't get to image anything but this. So every clear night from basically May until September, I had a small refractor out there, and I took the heart of Cygnus, right? So this just goes to show how much nebulosity is in Cygnus. I guess I could keep working on this, but the blue is oxygen, and this area is unusually bright in terms of ionized oxygen, oxygen 3. You can see there's a North American nebula and the Pelican Nebula, the clamshell nebulas on the far left. You can see down in the lower right, there's the Crescent Nebula. You can see just that whole area just filled with ionized gas. Okay, so those are emission nebulae. Those are ionized hydrogen that's just out in space. But sometimes we get the same effect from stars that are in some form of exploding. So planetary nebula will cover, planetary and Wolf-Rayet stars will cover first. But I wanted to show you, again, speaking of narrowband, right? So I showed you earlier this image of the Ring Nebula on the left. But on the right is if you add in, I took an H-alpha filter and took long exposures there, and you can reveal there's actually a lot more structure. And the reason you don't see it on the left is because it's just really, really faint. And the background light is overpowering it. If you use a narrowband filter, like on the right, you're only looking at the H-alpha, and you're able to then pull that out of the background. But yeah, the Ring Nebula actually has an outer shell, and I've seen online people taking even deeper images of this. There's actually a shell outside of the shell. But these are stars that are effectively expelling their outer layers. This is the biggest planetary nebula out there. This is the Helix Nebula. And again, just for comparison, on the left is a normal color RGB image. On the right is a narrowband image. And what's interesting here is actually, it's not all that different, but you can see cool little like striations. It looks very much like the iris of an eye, like those little stripes or scratches almost in it that are much easier reveal in the narrowband image. But planetary nebulae are also narrowband objects. They're only emitting at specific wavelengths. This is, I'm pretty sure this is actually the closest planetary nebula to us. This is Sharpless 216 on the left. But you can imagine this is a very old planetary, right? You can imagine this has just gotten more and more, as it just expands, getting fainter and fainter, and more diffuse. Kind of looks like it's expanding more in one direction, or maybe in that direction it's sort of hitting more matter in the interstellar medium or something. But I'm pretty sure Sharpless 216 is still thought to be the closest planetary to us. This is actually quite large in the sky. One of the prettiest, Sharpless 308. You should be able to see why they call it the Dolphin Nebula. Looks like a bottlenose dolphin's head. And you can see it's almost entirely ionized oxygen, which is great, because if you want to look like a dolphin, it helps that it's blue. And you can see the little patches of red. So that's the ionized hydrogen there, but it's mostly ionized oxygen. And this I took last month. This is from August. So you see the WR designation on the left, WR134. It's a Wolf-Rayet star. Or really, it's not the star you're looking at. It is the expulsion of a stellar wind and collision with the interstellar medium that you're getting that really cool arc. And then on the right is the Tulip Nebula. So I thought, again, did a little research online, looked at my field of view, said I can squeeze both these into one image, put those together. So this was actually, I think this took 3 nights of exposures to get this all together. The Crescent Nebula also has a Wolf-Rayet star at the center of it. Very cool in that the oxygen shell, you can see in blue on the outside, just this very thin shell, and then on the inside, the hydrogen and sulfur has this ripply, almost looks like a brain or something, this very cool ripply effect. So it gives it a very unique look. Thor's helmet also has a Wolf-Rayet star in the middle of it, and this is where I'm guessing there's just varying densities in the interstellar medium, and it's colliding with it, and you're just getting motion and more motion in one direction than the other, and you end up with this really interesting shape. But again, these objects, you can image them with a regular camera, but you really need the narrowband filters to pull it out, because they're really only emitting just at a couple of wavelengths. Okay, the last and maybe a little more rare type, these are stars that are not, these didn't expel their outer shells. These stars pretty much exploded. Most of the mass of the star exploded. So the classic example of that is Cygnus Loop, right? So a lot of you may have imaged these. So this is the veil, the different veil nebulas, eastern and western veil, the Pickering's triangle in the middle. Absolutely beautiful, super bright. Honestly, you can point it's I remember one of the first objects I ever imaged, and you point a Canon DSLR attached to a telescope, and it's right there. Like you see it immediately in the image. It's very bright. This one you will not see immediately. So this is about a 100-hour exposure.
Wow.
So this is, and I put in the upper right, that would be the size of the full moon. It is big, and it is extremely faint. It does not have a fancy name. It is G65.3 plus 5.7. I don't know that anybody's come up with a great name for it. People try to call it the Garlic Nebula. I'm not sure if that's sticking, but I think I was the 2nd or 3rd amateur to post an image of this in 2015. And technology has expanded so much, I feel like there must be dozens of images of this now on Astrobin. But it is incredibly faint. It's in Cygnus, right? It's overhead now, but it's really, really dim. Here's the Spaghetti Nebula, another really dim one. So this goes by Cineis 147, named after the observatory where it was, I guess, originally discovered in Crimea. But it's very faint and really has a cool, it really does look like spaghetti. Like it's kind of got these little strings in it that are very cool. All right, so those are supernova remnants. This is one more. I think this one fits the moniker of Garlic Nebula better. This is CTB1. This was discovered originally as a radio source, and then it looked. If you expose long enough, you can reveal it. It is also very, very faint. Okay, so let's go to gases that are not ionized. Right? So these are neutral gases. What you're going to see now are reflection nebulae, dark nebulae. This is where light is simply either being reflected off the gas, or the gas and dust is obscuring the stars behind it. The classic example, right? How could we not? M45, Pleiades. This is absolutely beautiful. I come back to this every year. It seems to reward you with deeper and deeper exposures, just more of those, little bands throughout it are just absolutely beautiful. But you can see, there's dust in that whole area of the sky, well beyond it. And the deeper you expose, the more you see. The Iris Nebula. So this is a great example of
Iris?
both types of nebula we were talking about here. It's the reflection nebula as well as a molecular cloud or a dark nebula. And you can see, they're the same thing, right? This is gas that's not being ionized, generally because the light being emitted by the stars isn't high enough energy, right? So it's more in the outside of UV, it's more down in the visible spectrum. Doesn't have enough energy to dislodge photons, so you end up with non-ionized gas. And you can see it's all one cloud, but where it's being brightly lit, essentially you get a reflection nebula. Where it's not, you're getting a dark nebula. And the whole thing is just a big molecular cloud. Iris Nebula, this is mislabeled. This is the Cocoon Nebula. I mistyped that. This is the Cocoon Nebula. So you've got a beautiful nebula over here, and then you've got these, that's not an absence of stars, right? So when you see a dark nebula, you're not seeing, there's not a hole there. What you're seeing is gas in front. The stars are just as dense there, but you've got something in front of it that's blocking your view. That's very, very cold. The coldest spots in the universe are actually within these molecular clouds, right? These are extremely cold, dark places. This one actually is the most recent image. I just took this, goodness, like 5 days ago. Not the most interesting object, but this is Barnard 174 in the middle. I was just looking for something interesting to image up there. But you can see where some of the gas is being ionized over on the right? So the dark nebula you see is obscuring the stars behind it, and it's not ionized. But then you see that pink over there, and that's where you're actually getting a UV star that's able to ionize the hydrogen out there. The Snake Nebula, this is Barnard 72. Took this with Max Whitby. Really does look like a snake, doesn't it? And then my favorite dark nebula of all, partially because it's pretty, partially because, talk about a name that sticks, this is the Dark Doodad. It has a Sandquist designation of Sandquist 152 or something. Nobody calls it that. It's the Dark Doodad. That is just the coolest name. But the cool thing about it is, I like how you can really see it's both gas, it's obscuring the stars behind it, but you can also see there's enough light there from all those Milky Way stars that is kind of causing the whole thing to glow, and you get that cool brown glow around the edges. But just a very cool. This is in the southern hemisphere. We cannot see this from here. And the dark shark. So this is in the northern hemisphere. This is in Cepheus. You can image this in the fall and winter. I think it's pretty cool. It really does look like a shark come just diving down out of the sky. And again, for that sense of depth, there's a galaxy up there, right? That spiral galaxy. So this dark shark, pretty close. This is actually not very far from us. That galaxy is way, way, way further, thousands of times further away. All in the same image just because they happen to be in the same line of sight. So when I was putting this talk together, I thought, is there a place in the sky that has all of these things? I don't know if there's any place that has all of them, but there's one place that's got a lot of them. So you got a globular cluster, open cluster, emission nebulae, reflection, dark nebulae, and a lot of color. So my favorite area in the whole night sky has all of these. This is the Rho Ophiuchi area. That is this area. Absolutely beautiful. Tough for us to image here because it's down. It's a little too far south. It'd be just almost on the horizon most of the time. But you got the blue horsehead on the left. You got this, you got a M4, the globular cluster. Antares is the bright yellow star there. You got ionized, gases. It's just kind of got it all in one place. Absolutely stunning. This streaming dark nebulae. But you kind of gives you a sense of the astrophysics of it all, right? So you've got those dark nebulae. You've got a lot of dust and gases, and then in some places where they get close to a star that's young and emits UV light, it's becoming ionized. In other places, it's blocking the stars. In other places, it's being illuminated, kind of all in one spot. Okay, so I just wanted to talk about where you can see these things. So as a framework for this, I wanted to use this image. So this is an image. This is the whole night sky. So this is what I've got the light panel up here with that on it. And I've got the posters with it. And Max and I also use this as kind of the framework for our book, The Visible Universe. But this was a project gone awry where we thought, oh, let's take a big mosaic of the Milky Way. And then we kind of just kept going. So we might as well finish the whole night sky. So we took this over 2 years. We had telescopes in Spain, in Chile, and the UK. This was done actually with a telephoto lens. Actually, it was a wide-angle lens. 153 panels. What you're seeing here is I've taken a regular color image, so we took red, green, and blue exposures to create a normal color image, and then in red we also overlaid H-alpha because that indicates where the nebulosity is, so where those ionized gases are. So just to orient you, I've put the constellations on here, and to think about all the things that we've seen tonight, where are they, right? So you can see the Milky Way, right? That is our galaxy. You are in the galaxy and you are looking out the plane of our galaxy. All the things we talked about, remember I told you, anything that's not a galaxy is in our galaxy, and so you can see them right there. So most of the things that we've seen tonight are actually really, really small in this image. But you can see there's a lot of nebulosity. All those red patches they follow the path of the Milky Way. The Milky Way looks like this because of the projection, right? This is an artifact of taking a 3D sphere and trying to smash it down onto a page. You're going to have some distortion. So like any map, it's got that. But you know that when you look out at the Milky Way, you're looking out at a plane. So it's not actually shaped like a U, but this is when we map it out, it looks like that. But you can see the nebulae follow that because they're all in our galaxy. They're hard to see on here, but the globular clusters and open clusters do as well. But globular clusters tend to be in orbit around our galaxy, and so they stick fairly close to that band. The point I wanted to make here is that these objects are in different parts of the sky because some are in our galaxy and follow the path of the galaxy. But when we look at other galaxies, right, they're not going to do that. Actually, our galaxy stands in the way. There are probably hundreds, millions of galaxies we cannot see because our galaxy's in the way, it's blocking us. But right in the center there, right, you see Virgo, you see Coma Berenices, what heck, I'm always going to say that wrong, but the Coma cluster is there, the Virgo cluster is there, right? That's spring. When Earth moves such that the night sky is facing away from the sun and toward Virgo, you are looking away from the center of our galaxy. You are looking toward other galaxies. And that's why spring is galaxy season. And you're going to see all those galaxies. So they're up in Ursa Major, right? All those areas, it's rich with galaxies, just simply because we're now faced away from our own galaxy. In summer, we tend to be looking toward the center of our galaxy. And that's why you're looking at all the nebulae there. And that's like nebula season almost. Okay, so I think we've talked about everything that we can without going into really deep astrophysics or anything. But I hope this image was helpful to sort of give you a sense of where everything is. I think you need to, if you can manually advance to the next slide. I think it might be my last one. There we go. Okay, so that's it. I'd be happy to answer any questions. And like I said, happy to chat after. I've got some books up here if you guys are interested. But yeah, any questions?
Sure, I had one question. And one big image you did that was a wide area, I think you said it was like 6 panels or something like that. Not seeing a lot of stars. Are you like removing the stars so you can see the nebulas better?
No. So it's an artifact of the narrowband filters.
Oh, okay.
So stars appear much more focused and dimmer in images with narrowband filters because you're blocking 97% of the spectrum and just letting like 1 to 3%, just a tiny sliver of it through. The nebula only emits that frequency. So it's all getting through, but you're blocking 95+% of the star's lights. And so that actually increases the prominence of the nebula just by virtue of the filter.
Makes sense, thanks.
Yeah. Mm-hmm. Yeah.
The photos you did of the dark nebula, can you rely at all on narrowband, or do you really need dark skies?
You cannot rely on narrowband. It won't help you at all. Yeah. So those are brought here because that's reflected starlight. So it emits at all wavelengths. So yes, you need. If there is anything you need dark skies most for, it's the dark nebulae molecular clouds. Yes. So a couple of those we gathered the data. I mean, I've done some from my backyard, the better one, the brighter ones. But yeah, the skies of Chile, I was absolutely amazed. In collaboration with 3 other amateur astrophotographers, we set up a telescope down there at Deep Sky Chile, and it was amazing to me because trying to image dark nebulae from here and taking 18 hours of exposures and barely revealing them, and then under the dark skies of Chile, it was like 2 hours and they were even better than I'd ever seen. Yeah, dark skies are absolutely essential.
Is there essentially nothing outside of sulfur, hydrogen, oxygen?
There are lots of other things, but so there's neon, there's helium, there's carbon monoxide, there's all sorts of things, but they are either A, in the visible spectrum but really, really faint, or B, when they reionize, they emit an ultraviolet or infrared, and we can't pick them up with our cameras. So the camera sensors are fairly close, actually. Their receptive range pretty close to the visual spectrum, and so yeah, it just doesn't do us any good.
So for us imagers, you're really not missing anything outside those 3?
No. The only potential exceptions are some planetary nebulae will have slightly different features in helium and nitrogen. So nitrogen 2 is the primary nitrogen wavelength in the visible spectrum. It is so close to hydrogen alpha that you need a 3 nanometer filter to split the two out. And the fact that you're going to be one of the 10 people a year who probably orders a nitrogen 2 filter means it's going to cost you. But even if you look at the images, it doesn't seem to reveal. So there's like, 10 planetary nebula you might get to use it on, and it doesn't really seem to reveal anything groundbreakingly different to me. So the answer is not really, not worth the effort. Yeah.
There's a lot of different kinds of nebulae in your photos,
Yeah.
and some of them, okay, you have the supernova remnants, and then you have things from dying stars like the Ring Nebula.
Mm-hmm.
Is it possible that some of those dark nebula are, let's say, supernova remnants from so far along in time that we don't really recognize them as that, or how do we
Yeah.
identify what they are?
So, the universe has been around just long enough so that in a lot of areas you've had multiple cycles where stars were born. So you formed, the Big Bang, you form only hydrogen, helium, and a trace amount of lithium. That's all that's formed. Then stars form, and the compression of stars can form elements up to iron. Then, to form any element that's got more protons in it than iron, you have to have some sort of massive explosion or a lot of energy. So we've gone through several cycles of this since the beginning of the universe, where you've got stars that are composed of multiple prior generations. So you've had stars form, explode, that dust has been picked up, scooped up, formed into a new star, some of those exploded, and so yes, that's how actually the heavier elements actually even get out into that. So those molecular clouds are typically star-forming regions. Any of the heavier elements are certainly from prior star explosions, and some of the molecular hydrogen in there could be. There would be no way, I guess, to separate those out. But yeah, the universe is kind of a soup of this now, of where we have multiple generations of stars already. So it's all mixed together. I don't know what the proportions exactly would be, but yeah, anything like the carbon monoxide and things like that, I mean, that's very likely from a prior star explosion. Yeah.
Okay, I wanted to ask
Yeah.
your first image. What was it and when was it that you took? And was it with film or was it with digital? Do you remember?
So I came of age in the digital era, so
Okay.
I guess, okay, so technically my first astrophoto was not a deep sky object. It was a modified webcam in 2001 with a picture of Jupiter.
Oh, okay.
That was when I was absolutely blown away that you could take a consumer off the shelf and had a teeny tiny little, smaller than an eraser head size sensor on it, and you could modify them and take them apart and use them for planetary images. That's technically my first one. My first deep sky object, I'm pretty sure actually was very cliched. It would have been the Orion Nebula. So I made a common mistake. I had grown up reading Sky and Telescope, and you see these ads for these Schmidt-Cassegrain telescopes. You're like, oh, I got to get one of those. And so I thought, I've always wanted one. I bought one, and I used that actually to take a picture of the Orion Nebula. But I quickly learned Schmidt-Cassegrain's really not your best choice for imaging. Small refractors are far, far better. So within a few months, sold that on Astromart. I bought a small refractor, and then I went back to the Orion Nebula and actually took a much better picture. But that was with a Canon SLR, unmodified, off the shelf. Took a Canon DSLR, you attach a T-ring to it, you put it in the eyepiece holder, right? Worked like charm.
Yeah.
Yeah.
You got any thoughts that, we get a lot of people come and say, yeah, I'm interested in getting into imaging. They see all these beautiful pictures and things. To those of us that have gotten a little into it, we have a pretty good idea what's involved.
Yeah. Involved being the key word, yeah.
Or committed. Anyway, you got any recommendations to those who think they might want to get into it?
Yeah. So it's this. You'll see this on the internet a lot, but it really is tried and true. You will save yourself a ton of frustration with just an 80 millimeter refractor, some small refractor, and a DSLR. And the reason for that is refractors are light, a lot of the things that you've seen, they're big. Like magnification is not the game here. You're trying to reveal faint things. So you're not looking for the biggest telescope with the longest focal length. Therefore, a short focal length telescope, it's, longer magnification is going to, or longer focal length is going to magnify any motion, right? So if you're a visual observer, you've seen this, right? So if you tap a telescope that's a long focal length, like everything just moves like crazy because you just magnified it in a tiny bit of the sky. Short focal length, much more tolerant to that. So refractors are just so easy. They're so cheap now. You can get a great 80 millimeter refractor for like $350 now. You can get a used Canon DSLR for a couple $100. T-adapter, something to put that together. And then you really do need an equatorial mount. You need something that's going to follow the rotation of the sky. Those have even gotten so much cheaper now. So for $500, you can get a decent equatorial mount. So for around $1,000 now, you can have a great kit. Will last you for a couple of years probably. And then, only then move up to longer focal lengths, bigger telescopes, better mounts, things like that. But I'm convinced that, it can keep you busy for at least a year. A small refractor with a DSLR and all the stuff that's passing, by the seasons, there's enough big, beautiful, bright things out there that you can take pictures of. And then decide if the hobby's, okay, do you really want to commit the time and effort to go deeper?
Thanks.
Mm-hmm.
I had a revisiting the filters real quick.
Yeah.
I just thought about hydrogen beta filters. What's your impression on those?
So hydrogen beta filters are used in visual astronomy. So the hydrogen beta emission line is typically fainter than hydrogen alpha. And it's used though because the eye is more sensitive to that end of the spectrum for visual. It's actually not used in imaging because you're going to see the same areas of the sky. So the hydrogen is ionized in the same place. So it's the same ionized hydrogen emitting the H alpha in red and H beta in blue. So why would you choose the fainter of the two emission lines? You're going to see this, it's going to light up in the same spots in the sky, right? So we use H alpha for that reason, just because it's brighter. But in visual, you use an H beta filter just because to the eye, it's far more sensitive in blue than it is to red. And so actually, if you were to look through an H alpha filter, it would look dimmer to the eye. Yeah?
How do you feel about the tri-band and dual band filters?
So I think they're a great way to get started if you have a one-shot color sensor, so a sensor with a barrel rate, like a DSLR. I think it's a great way to get started, but it's quite limiting because ultimately H alpha for almost everything, outside of planetary nebulae and a couple emission nebulae, the H alpha is going to be 3 to 10 times brighter than the oxygen 3. So if you have a tri-band filter, and that applies to sulfur as well, so the hydrogen is going to be far, far brighter than sulfur. So what I can do is I can put one filter in front and I can take, let's say, a certain amount, 2 hours, let's say, of hydrogen alpha, and I can put the oxygen filter on and take 8 hours of that. I can do that because I'm taking different filters. If you've got that filter in front that's a tri-band filter, yes, it's letting those 3 in. However, you can't control your exposure time now. You got to take the same amount of all of them, and the oxygen is just going to always be much, much fainter. The other thing is, inherently, light's passing through one filter, then, because you're using a color sensor there's a tiny little color filter on each pixel. It's got to pass through another. There's just loss at each of those stages. So I think it's a great way to get started, and I noticed that the objects that they use for the ads for those are the few that are naturally very bright in oxygen, and it looks great. It's a little harder to work with for most narrowband targets, but it's a great way to start. I think all that's going to end up happening is if you only have a color sensor and you try one of those, I feel like eventually, if you're doing that, you're going to like it, and you're going to go to a mono sensor, and you're going to go to separate filters at some point. Yes?
Again, along the filters, I got 2 questions.
Yeah.
If I can get them both.
Okay.
So as I was learning, I paid a ton of money for a quad narrowband.
Mm-hmm.
And, it made nice OSC images because it cut out a lot of light pollution.
Yeah.
I've recently found that I've gone to RGB and it makes a really nice luminance channel.
Yeah.
And now the question is, do you really need the quad though? Would an HA do just as well as a quad for luminance when you're doing?
It depends on the object, right? So a lot of objects you saw that I was showing you, HA and sulfur would appear in pretty much the same spots, and that would be one structure. Oxygen is typically, if it's present in an emission nebula, is typically in the core and far more diffuse with very little structure. And so if you were to add H alpha as the luminance to it, you would miss the oxygen essentially, right?
But there are dual bands too,
Yeah.
where you can get HA and oxygen, and they're a lot cheaper than a quad band.
Yes.
And that would be a good luminance?
That would be a much better luminance, yes.
Okay.
And again, only for emission objects,
emission
right?
nebula,
Yeah, don't
yeah.
point these at galaxies and expect it to get better. It's actually gonna make your image worse.
So the other second question, and I'm
Yeah.
sure Lynn has an opinion on this too, but, so I've done OSC, I've done RGB, I have not done narrowband. Is there the concept of luminance of narrowband, or do you just shoot the narrowband and that's it?
There's not really the concept of luminance.
Okay.
Yeah. So the closest thing to it is I have seen people trying this where they're like, oh, I'll take a tri-band filter and I'll put it on there and I'll use that as luminance. I don't see the point in that because you are you're going to inherently stretch the oxygen and sulfur more in almost every object. You're actually going to stretch those channels more so that they are revealed. Otherwise, your images are you just see the hydrogen all the time and it would overwhelm everything. So so the idea of sort of pulling a luminance in, I don't know. I'm not sure. If you did do it though, a tri-band filter would be the way to go. But time is so precious anyway.
Weighing your SHO rather than trying to add luminance.
Exactly.
Okay.
Yeah.
Thank you.
Yeah. Yes.
I'm very new to this. You spoke about a telescope in Chile. Was that something that you owned and placed there and set up there, or did you rent the ability to use it from from a different area?
Right. So great question. Both options are out there. So there are services out there like iTelescope, and I forget the name of some of the others, but there are several out there. It's like Rent-A-Scope, right? Where you buy minutes on a scope, and you sign up to use it a certain night. This was not that case. We put it at a remote hosting facility. So Deep Sky Chile basically charges you rent for a pier, and you have to fly to Chile and set up your scope. So you ship your mount and your scope and your camera and everything down there, and then you can go there. In this case, Max got to go. I didn't get to go to Chile. I was so mad. But my co-author Max went and set it up. I think you can actually pay them, and they'll set it up. They charge an hourly rate. But we actually set up that scope there. And then it's out in the middle of the Atacama Desert, and you're thinking, how in the world do they have internet access? And believe it or not, they have 5G. So they literally have a SIM card set up for every pier, and you run your telescope all night, and then you dial, you connect in the next morning, like your remote desktop into your computer, because you put a little computer there too, and you can then download all your images the next morning. It's fantastic. It works unbelievably well. You occasionally do have something like, oh, Windows installed an update I didn't want it to or something, and there are people on site, and you tell them, hey, can you go out and reboot my computer or check on it? So yes, we did actually put a scope in Chile. Yes.
This all sounds very familiar to me. Was there a book review that I read or an article in Astronomy magazine or something about your photographing the entire Milky Way?
So I don't think we've been in Sky and Telescope. We were in Amateur Astrophotographer magazine, I think, recently. There was someone else who did this, Axel Mellinger, in 2012-ish, I think. But no, but I'm on YouTube, and I've done a talk about this for 6 or 7 different things. So if you're on YouTube, you may have seen a video about it there. But no, not that I'm aware of. Maybe, but my subscription has lapsed to Sky and Telescope, so maybe they talked about it and I didn't know about it.
I remember hearing about that too. Was it? Did you take out Facebook ads or something?
No, we've never advertised at all actually for the book or the poster or anything. So yeah, honestly, just word of mouth. I'll put it this way, if any of you are thinking of making your living in astrophotography, it's not really possible. This is not my day job. I have a normal like corporate day job, and this is my side gig. So no, really, if we advertise, it would probably. I mean, I don't know. It might help, but it's a kind of a small community, and advertising costs a lot of money. So I would love to know what. Now I'm excited. I have to go figure out what you guys are talking about, because maybe word has gotten out. But I've done a lot of YouTube talks that are about this. Yeah, you first.
You have prices for all those books. Do you have a price for that sky? Because that's like really hard to buy around.
That sky? Priceless, my friend. Priceless.
Yeah.
Yes. No, I would never let go. That's the other great thing about Chile. 300 clear nights a year. You know, I think. Yes, it's unbelievable. And not only clear nights, but like you said, low humidity. It is unbelievable. It's like being in space. Like it's like nothing else. Yeah, we get like 40, 50 clear nights around here. I feel like a year. Absolutely bananas in Chile. Yes.
Yeah. Can you talk a little bit about how you're mapping the narrowbands to what colors and?
Yes. So that's
Do
standard.
you use different mappings and?
No. So this kind of the standard that has the astrophotography community is aligned on is the Hubble palette. So that's SHO. So sulfur to red, hydrogen to green, oxygen to blue. So that's pretty typical. People have tried other palettes. If you map them to other combinations, there's the French Hawaii Canada telescope palette, you get a lot of purples and greens, and it looks weird to people. I think it just, I don't know. Maybe it's taste, maybe it's what we've gotten used to, but that's kind of what we've fallen into. Now, once I've done that mapping, there are some tricks that you can do to sort of pull out the green so that you get that more typical blue-gold kind of look. Because there actually really isn't any green in space. Outside of planetary nebulae, there's no green out there. The Planck curve does not pass through green, and so people even inherently or just instinctually perceive that as a weird color to see. So you have to take the SHO image and tweak it a little bit color-wise by pulling the green toward either blue or red to get a more pleasing palette. So that's called the people talk about like the gold teal or gold blue palette, but it really starts with the same SHO to RGB mapper. I see very little. The only other one that people do is HOO. So sulfur, like I said, sulfur is typically in the same places in the nebula that the hydrogen is. So a lot of it's not adding anything new sometimes to add it. So you can just take hydrogen and oxygen, and you map oxygen to both green and blue. You map the hydrogen to red. That works for a lot of objects as well. That's the main ones you see. You see H added to an RGB image as red, but yeah, as far as like rearranging them, not too often. Yeah.
Your Chile telescope, you're talking about how much more dark it is there.
Yeah.
And then you mentioned the Atacama, and I'm thinking that altitude probably isn't a factor there.
Yeah, they're all at like 10,000 feet. So the whole desert is like at 9,000 feet, and then like these are on a rise. I think they're about 10,000 feet.
So then it is a factor.
Yes.
Okay.
Yeah. So I mean, that whole desert just rains there like once a century in parts of it. So it's incredibly dry. But you're in a desert, so the humidity is just incredibly low. The light scatter is low. I noticed that when the moon is out, if you don't see the same kind of sky glow, there's just less for it to reflect off of. So yeah, it's mostly due to the desert, but yes, the fact that you're at that altitude, there's just less air mass above you at that point.
I think you get skin cancer in about 10 minutes on a sunny day.
And you'll be out of breath in 10 seconds. Yeah. All right. Well, thank you guys so much for having me. I really appreciate it.